Hey folks, in this video, I'm going to show you how to perform a hypothesis test around the standard deviation using the chi-squared in Microsoft Excel. This is a little different than our normal hypothesis test, and it is 100% around the fact that we're using the chi-squared distribution, which makes our calculation of the critical values and the test statistic a little different than we were doing with previous hypothesis tests. We will not be using the p-value method in this. We will be using the critical value method. And what you'll see up here in the upper left-hand part of this screen, this is going to be my reference anytime I'm doing this kind of hypothesis test. I want to be very, very sure to take a look at this diagram, because if it's a left-tailed or it's a right-tailed, or especially if it's a two-tailed, these tests are vastly different. So I just keep this up and I keep this handy in my hip pocket if I ever have to do any of these problems. This is the problem we're going to be doing. So scores of an IQ test are normally distributed. This is great. They have to be normally distributed for us to do this hypothesis test at all. A sample of 25 IQ scores with a standard deviation of S equals 8. Great. I could start pulling out some of the things that are really important in this problem. I know N is equal to 25. I know S is equal to 8. The developer of this test claims that the population standard deviation, sigma, this is going to be my sigma naught, so just keep that in mind. Their claim is sigma naught is 15, the true population standard deviation. So sigma naught, notice that I changed it there, I didn't write sigma, is equal to 15. Do these data provide sufficient evidence to contradict this claim? My alpha equals 0.05 level of significance. The alpha is also very important whenever you're doing these problems. So alpha equals 0.05. Okay. So the first thing that I need to do is I need to take a look at this and I say, well, which hypothesis test I'm doing contradicts this claim. That is an indication that they're saying, hey, is it just not equal to 15? So my null hypothesis is always the boring one, sigma equals 15. This is what was stated. My alternative hypothesis for this one is sigma is not equal to 15. So this tells me this is a two-tailed test. I did this on purpose because this is just a little more complicated. You'll notice I have three different values. I got a chi-squared value, my test statistic I have to calculate. Then I have two critical values, my chi-squared alpha over 2 and my chi-squared 1 minus alpha over 2. So let's start putting those pieces together. First, I need my alpha over 2, which is 0.025. I'm also going to let the calculator calculate this, because guess what? We're going to put together a template for this, ladies and gentlemen. Let's go ahead and move over to our calculator. Okay, I'm going to move this to the side. That to the side. Move this over here so we can still see some of these values. What's important here mainly is going to be our N, S, sigma naught, and our alphas. Those are going to be the important things. In order to do this problem, what do I need? Well, I need sigma naught, I need S, I need N, what else? Alpha. And I'm going to do a couple of things with alpha to make it easier as I go along with my template. I'm going to do alpha over 2. You don't need this for all of your templates. If you're doing a one-tail test, you wouldn't do alpha over 2. And I need 1 minus alpha over 2. I need 2 chi-squared critical values. So this is my critical using alpha over 2. And then this is my critical value using 1 minus alpha over 2. And what are we going to compare that against? We're going to compare this against our test statistic. What's nice about this is we don't have to do any type of probabilities or any type of manipulation with the test statistic. We just compare it against these two critical values. So this is my test stat. Notice that I have the test statistic up here in the upper left-hand corner. This is what we're going to be calculating for our test statistic. So let's start putting some of these values in. My sigma naught is 15. My S is 8. My N is 25. Alpha, 0.05. Now remember, I always like to highlight in yellow the stuff I have to input. The stuff that's calculated, I'll just leave normal. So this is equal to this 0.05 divided by 2. I'm going to leave this in formulas view until we get a little further on so you can copy the formulas down. This is equal to, now I can be a little bit lazy because I've already done alpha over 2, 1 minus the top value right here, this B5, blam, okay? Now, to calculate the critical values, I have to use the chi-square distribution. There's something I didn't add in here. I might as well add because we have a nice little template going on here is degrees of freedom. My degrees of freedom are n minus 1, so it should be 24. So it's 25 minus 1. But we like having a template, and I don't like putting in the fewest amount of values possible. All right, let's go ahead and do the critical value with the alpha over 2. This is equal to chi sq dot inverse. Now, this is a little different than anything we've done previously with the hypothesis test. I'm always going to use the RT. I'm always going to take the area on the right side of the chi-square distribution. I'm not going to draw the chi-square distribution. A lot of times that leads to a lot of confusion, but you always use the .RT when you're calculating these chi-squared hypothesis using this method, okay? My probability is going to be, remember, it's alpha over 2, that matches right up, and my degrees of freedom is something I just added right there, well, blam, okay? This one is going to look almost the exact same thing, chi-squared dot inverse dot RT. These are going to give me numbers back. 1 minus alpha over 2, 1 minus alpha over 2. That's why I'm very clear when I annotate what is in my template here, comma, and then degrees of freedom, same thing. These are going to be two numbers, and they're going to be pretty far apart, and they should be. If our test statistic is in between those two, that's the easiest way to look at these two tails. If it's in between those two, I fail to reject the null hypothesis. Let's take a look at these before we go any further. Look at that, 39 and 12. If this test statistic is bigger than 39 or less than 12, then we reject the null hypothesis. If it's between those two values, we fail to reject the null hypothesis. Go back to formulas. Let's calculate our test statistic. Our test statistic for this is, I would say, just a little mathematically simpler than some of the other test statistics for a hypothesis test. So this is going to be n minus 1. You could always use degrees of freedom, but I'm not going to. I'm going to use n minus 1 times s, right here, s squared, divided by sigma naught squared. Order of operations means this will happen in the order I want it to, so I'm okay with not putting any parentheses around there. Let's go ahead and look at that. That test statistic is much smaller than this critical value, so we are good to reject that null hypothesis. What are we talking about here? This is the 1 minus alpha over 2. The 1 minus alpha over 2, our chi-squared is less than the 1 minus alpha over 2. It meets the criteria of one of these two situations. Therefore, we reject the null hypothesis, and we say that less than 25% of the population have tattoos. Thank you very much. Make yourself a template to help you out a lot.